talking about tetra for us.
Well, it's working. Thanks everyone. Just a warning before I get into the actual talk. If you've been to pH Neutral, I've given a fairly similar talk there. If you've listened to that talk, I strongly recommend you attend a different lecture or you enjoy yourself at the campsite. But I guess there's very little point if you've seen this at pH Neutral or at Easter Hag. Then I suppose you have more important things to do with your time than to listen to this yet another time. This talk is about research into tetra security, or rather, let's say, research into the real-world security configurations or lack thereof in tetra networks that can be found. So this is not really a detailed discussion about all the possible security mechanisms inside tetra, but more like what do we see in the real world outside of the specifications. Okay. So, well, I skipped the introduction about myself. What's tetra? Tetra is terrestrial trunked radio. It's a specification for digital professional mobile radio, PMR. It's standardized by ETSI, European Telecommunications Standardization Institute, in the early 1990s. So it's something like, I would say, 5 to 7 years after GSM. So it's definitely a later standard than GSM, but it's specified by the same standardization institute. The first release of the specification came out in '95, and it's endorsed by the European Union Radio Communications Committee. To be honest, I don't really understand what's the official function of this committee, but I think by endorsing something as official European Union standard, I suspect there may be some implications on use and deployment by governments in the European Union. There's a number of commercial vendors that sell equipment, both for the network side as well as for the handset side. Motorola is one of them, fairly big in that market. There's also EADS, which has bought the Tetra unit or the Tetra business unit from Nokia because they didn't do Tetra development by themselves originally. And then there's a company that keeps changing its name every 2 to 4 years. It was called Philips initially, then it became Pi Communications, then it became Simoco, and finally now it's called Artiva. It's all the same. They just change names more often than you can actually follow. Then there is Rode & Schwarz, a very infamous German company, who also are fairly big in the Tetra market. And there are some Chinese vendors that are expected to appear with Tetra products on the market very, very soon. I've spoken to some of them. Interestingly, at least officially, they claim they need to build their own devices because they're subject to crypto export regulations. So Chinese, if somebody in China wants to operate an encrypted Tetra network, all the European and US vendors, they're not permitted to ship them the encrypted version of the Tetra equipment, so they need to develop it themselves in order to have encryption, which, well, if you think about competition from the Far East, I think it's fairly counterproductive. So you create Chinese competition by not giving them the crypto they want. But, well, this is not about economics. As most of you probably know, I've done quite a bit of work on GSM in recent years. So for me, it's logical to compare Tetra with GSM. What are the similarities? What are the differences? Well, one fundamental difference that is always marketed also as an advantage of Tetra over GSM is that it's longer range due to lower frequency. If you know a little bit about radio waves and radio wave propagation, then lower frequency typically means more easy penetration into buildings, and the higher frequency you get, the more the propagation characteristics are like light. So in high frequency systems, like 2.4 gigahertz Wi-Fi, if you don't have direct line of sight, it's not very good. But with this low frequency range, the tetra is typically deployed for 110, 440, 450 megahertz. You have a lower frequency. However, GSM is also specified for lower frequencies, just nobody ever built equipment as far as I know. You have a higher spectral efficiency, which means you can get more speech channels into the same RF bandwidth. You can see that from getting 4 speech channels in 25 kilohertz of radio frequency space, whereas in GSM it's 16 channels on 270 kilohertz. Tetra is specified to work in with moving handsets at speeds in excess of 400 kph. It was an important requirement that even in the TGV or any other high-speed train, for example, the system still works reliably. In case you don't know, many radio systems have problems with the Doppler shift and other effects at high speeds. I think GSM officially is not specified for more than, I don't know, 120, 150 kilometers or something like that. It still works if you drive faster in your car in most cases, but that's outside of specification. That just means that your equipment is better than what the spec says. But Tetra is really specified to work at those speeds. It allows one-to-one, one-to-many, and many-to-many. Communication models. So it's not a telephony system where you have a strict one-to-one or maybe conference call scenario, but you have group calls and so on. However, GSM-R, the railway GSM version, ASCI, the advanced speech control items, it's not the ASCII code, it's advanced speech control items, they also permit that. The one real differentiation that I see is the direct mode, where handsets can communicate in something you could, in 2011 you would call it peer-to-peer. So they can talk to each other without having a centralized server or centralized infrastructure in place. That's called Tetra Direct Mode, DMO. And that's really something that GSM doesn't have anything like that. And another thing that's typically marketed is that its infrastructure is separate from commercial public networks, but the same is true for railway networks based on GSM-R. There's a decentralized fallback inside the Tetra protocols, which means unlike a GSM network, where when a base station loses the connection to the core network, it completely stops to provide any service to the subscribers. In Tetra, they have some mechanisms to make sure, even if there's some backhaul disconnect, the base station can still provide service to the local users, which is especially important if you think of natural disasters, earthquake situations, and so on. However, most of these things that Tetra can do, which GSM cannot do, require a lot of additional code, a lot of additional protocols, and even additional hardware. So it's a bit unfair to compare them with each other. I believe you could do the same with GSM by just adding a few bits here and there. But well, anyway. My personal belief is that the industry rather reinvented a completely different system called which is unrelated to GSM, to make sure they have different pricing in different markets and so on, right? If you would sell GSM to the police or something like that, and then they will of course claim, why do you charge so much for this GSM phone if a commercial phone is so cheap? But if you say, well, this is a completely different system, it's Tetra, it is different modulation, different protocols, and so on, of course, it's a special purpose market, the quantities are lower, you don't get into the economics of scale, so you can charge a much higher price for the actual equipment to the subscribers, which, well, is in the interest, of course, of the industry. So I think it's mostly industry politics that caused this to turn out the way it has turned out. If you look at actual deployments, there's a nice industry consortium called the Tetra MOU organization, and you can they have a website, and you can look at, I think they have every 6 months they issue a newsletter, and they will tell you what new deployments were made in which country, and how great Tetra is, and everyone and his mother now uses Tetra and so on. It's really marketing stuff, but you can get what kind of deployment numbers and figures you have. So 114 countries on the globe have deployed Tetra networks today, basically on every continent, including Australia, except North America. And that is a very simple reason, because in North America, for political reasons, of course, they have their own system. It's the APCO Project 25. If you go back in the past, the United States had their own TV standard. They have their own, even now with digital TV, they have a different standard. And also for police radio, of course, they have a different standard. Cell phones also, if you go back to CDMA systems and so on. So there's always industry politics that play a role in this. So in the US, Tetra is not being used. They use a different system. Now, what kind of users use Tetra? You have police, you have transportation services, military, fire service, ambulances, customs, Coast Guard, the typical customers of these systems. But also, what most people don't realize is that there's a growing number of private networks which are not related to governments or to government functions or any kind of government authorities. To give you an example, in Germany there are 63 registered Tetra networks, and only 5 of them are government related. It's called BOS, Behörden der Ordnung und Sicherheit, for those who understand German. As you can see, by far the larger number is used by commercial companies, private companies, not by the public sector. And now, what kind of companies are these? Well, you can think of harbor companies that operate large harbors and they need some radio system. You can think of industrial plants like chemical plants, power plants, all kinds of any kind of industry that occupies a large, they have large land, large facilities where a radio communication makes a lot of sense. I mean, if you have a company that only works in offices, well, you have desk phones, your VoIP phones or whatever, you don't need Tetra. But if it's some larger area that needs to be covered, Tetra seems a popular choice in recent years. So if you want to keep up to date, you can follow that newsletter. Interestingly, in recent years, it seems that almost all of the new deployments are in Asia, particularly in China. China is extremely big in Tetra deployments. Basically, every big city now has a Tetra radio for their subway system or for the police or for God knows what. So very, very large deployment numbers there. Frequency-wise, these are the frequencies that you will find in Europe. But Tetra can principally can work in any frequency. It's mainly subject to whatever the local regulatory body requests to be used. But in Europe, it's harmonized, and you will find those things. The two ranges, like 280 to 283 and 390 to 393, that's like GSM. It's uplink and downlink frequencies. There's a frequency spacing between what the handset sends to the base station and what the base station sends to the handset. The single carriers are 25 kilohertz wide. There are no guard bands, which means you can have, like every 25 kilohertz, you could have a different Tetra carrier. There's some other details. I'm going to skip them. They're not really that interesting. Interestingly, there is something called Tetra 2. Tetra 2 is not really an official term. It's more a marketing term. And it enhances the capacity, especially for data services, and it uses wider, it's basically channel bundling. So instead of using 125 kilohertz channels, it uses 50, 75, or 100 kilohertz of frequency bandwidth. I've not seen any of these deployed anywhere. I think it's mostly specified, and some companies sell equipment for it, but I think it's not widely deployed. Looking at the physical layer, the radio modem layer, the modulation is P-quarter differential quadrature phase shift keying. If you're not into communications, it probably doesn't really say much to you. Just very quickly, you have 2 bits in every symbol that's transmitted. The information is encoded in the phase difference, so that's why it's differential encoding. You have 8 phase constellations with 4 possible transitions. And it means that you have 18 kilosymbols per second leading to 36 kilobits per second on a single tetra channel. So it's very, very low speed if you look at Wi-Fi or any kind of more modern or commercial communication. This is how the constellation diagram looks like. Just very quickly, it's not really all that important. It's a time division multiple access scheme, so it inherits a lot of GSM, but does everything very different. So you cannot reuse any code, you cannot reuse any equipment. I mean, in theory, a lot of the things are the same, but in detail, so many things have changed that you cannot reuse anything. And I think that's the purpose of the entire system. So you have time slots, and every time slot contains 510 bits versus 156 in GSM. You have 4 time slots, GSM has 8. The duration is 56 milliseconds instead of 4.6 milliseconds. The multiframe has 18 instead of 26 multiframes, and so on. So the differences go on like this. But it's the same tree. If you look at the multiplex tree, it's the same tree. And even a lot of the channels have the same names, but they just have different parameters. If you look at the protocol stack, it's much more complex than GSM. There is a shared stacking on the lower levels. You have the physical layer, you have something called the lower MAC, the upper MAC, and LLC, logical link control. And above LLC, there is what's called the MLE. Trying to remember what MLE means. Actually, I forgot it, I think. It resembles the GSM radio resource layer, if you're familiar with that. And on top of that, you have things like mobility management, call control, connection-oriented and connection-less services. These are all buzzwords and terms and new vocabulary. Of course, every new spec has to come with all its new abbreviations and acronyms that you need to learn. CMCE is basically what CC, what call control is in GSM. CONS, connection-oriented service, is what circuit switch data is in GSM. And CNLS is what GPRS is or GPRS session management is in GSM. Yeah, if you look at the lower layers of Tetra, it looks something like this. You have a coded block with some CRC inside. There's a MAC block. Inside the MAC block, you have a MAC header and a MAC service data unit. Inside there, you have an LLC header and an LLC service data unit, and in there you have an MLE. At the MLE boundary, you have an LLC service data unit. So it's very, very logical stacking. Right? You have a header and some payload, and in there you have the header for the next layer and some payload and so on, and it goes all those ways up through a number of different protocols. If you look at it not in terms of stacking, but more in terms of how things are organized horizontally, you have these different entities. The idea is that here, where these arrows are, is your air interface. This is your radio interface, and then you have the mobile station, which is your handset, and you have the base station on the other end, and you have all these different protocol entities communicating with each other. And since it's specified very formally by ETSI, of course, you have the U plane, the user plane, which contains the actual speech data, and you have the C plane, the control plane for control. You know, it's all very, very well laid out and formally specified. Now, if we look beyond those technical details and look at security features that Tetra offers, well, the first thing I can tell you is all security features are optional, exactly like in GSM. So despite being a system developed specifically for a very security sensitive market, the police and government market, they did not make any of the security features a mandatory requirement of the specification. So like in GSM, everything is optional. You can do authentication, you cannot do authentication. You can do encryption, but you can also not do encryption. Right? And you can do end-to-end encryption, or you cannot do it. You can do air interface encryption, or you cannot do it. You can do over-the-air rekeying, or you cannot do it, and so on. So it's, again, lots of options, and you can implement Tetra without any of these security features, and it will still be a Tetra implementation. Furthermore, not all handsets support all those features, so you end up in problems with compatibility, and sometimes you settle on the least common denominator, which might not be the best in terms of security. The key material for authentication and encryption can be stored either in the handset flash memory or in the SIM card if the handset actually supports SIM cards for Tetra. Authentication of Tetra uses mobility management, just like in GSM. If you're familiar with GSM, you know that the authentication mechanism uses mobility management. The same here. Basically, of course, all the keys and everything have to be named different again. So there's the user authentication key, the UAK, which is sort of the KI of Tetra. And it generates an authentication key by use of algorithms, and the algorithms are, of course, not called A3 and A8, but they're called TB1, TB2, or TB3. And of course, everything has to have a T in front because T is Tetra. So, it's TA, TB, 1, 11, 12, and so on. So, there are 3 modes for authentication, and that's really an improvement over GSM. You can have either the authentication of the user by the infrastructure, which is, what you see in GSM networks as well. You authenticate the SIM card of the subscriber. But you can also have the authentication of the infrastructure by the user. So the user actually, or the handset of the user, has abilities to cryptographically authenticate the network. Good. And there's also mutual authentication, which basically just combines those 2 mechanisms. However, as indicated, if at all, and which of these mechanisms are used is again completely optional. This is a diagram of how the individual algorithms tie together. Not really going into the details here. It's all nice and well that they have specified authentication, they have specified encryption, but as you will see, many networks don't even use it. So that's why I'm saying, oh, okay, nice, you can look at it, and it's a nice exercise in analyzing a cryptographic system, but we don't even need to do that for many Tetra networks. Just to give you some more idea, while Tetra itself, the specification, you can download from Etsy, like you can download the GSM specs. Again, the ciphers themselves are not specified. So the Tetra encryption algorithms are not publicly specified, just like the GSM encryption algorithms are officially not specified, at least the older ones. Of course, they have been reversed meanwhile. For Tetra, I'm not aware of such an effort yet, but I know people who are working on it. So there are also all these other algorithms for key derivation, TA11, TA21, TA12, TA22, TB4, and all these small algorithms. They are all the specification has been published refers to them, but they're all black boxes. So you don't know how all these key derivations and so on work. So that's why I'm saying I think it's a very interesting system to be analyzed and waiting to be analyzed. But as I said, for many networks, you don't even need to do any of that. Okay, but still, what kind of encryption do we have? Well, the Tetra air interface encryption, once again, is like GSM. It only encrypts the air interface, the radio interface. It does not encrypt the core network or any of the backhaul links in your network. So it's just encrypting the last mile and nothing else. The difference to GSM is that it's not between layer 1 and layer 0, but it's actually inside the upper MAC layer. Which makes it much better design-wise, because it means you don't have idle frames that generate known plain text, and you don't have redundant information like we have in GSM, where you have forward error correction before you encrypt. In Tetra, they've done these things correctly, so you don't get any additional information for known ciphertext attacks, known plain text attacks, anything like that. The encryption happens with different keys. You don't only have a single key like in GSM. You actually have various different keys. I'm going to talk a bit about them. And you have, of course, an initialization vector that is derived from the numbers that define where in the TDMA time frame you are located right now. Well, this is schematically how the encryption works. But I mean, of course, this is just how the black boxes are tied together, not the contents of the black boxes that are involved. So the different keys. There's a static cipher key. That's the easiest way you can do a Tetra encryption. You can compare it to something like web shared keys or something like that, right? You have a pre-shared key that gets installed in every handset. You can store up to 32 of those keys in the handset, and then the network advertises which of those 32 pre-shared keys is to be used inside the handset. That's, of course, a very, very weak level of security. Nevertheless, it's specified in tetra. The next step is derived cipher keys, which is sort of similar to what GSM uses. So you have a SIM card or some hardware token inside the handset that contains a secret key that's not transmitted over the air interface, and then you derive a cipher key that's actually used for the encryption during the given session, and it can be regenerated. There's also a common cipher key which can be used for group calls. One of the features that Tetra has is, of course, group calls. And in group calls, the way how they're implemented, of course, the group needs to share the same key. Otherwise, how would they be able to talk to each other? So this is either done with one global common cipher key that applies to all of the groups, or you can have group-specific cipher keys using the GCK, or even you can have modified GCKs, which is sort of a even more sophisticated scheme. So all these different keys, they can be renegotiated by a mechanism called OTAR, over-the-air rekeying, OTAR. And the actual encryption algorithms that are specified are called TIA. I think it's quite funny. Most people think of the trivial encryption algorithm if they read TIA, but no, it's the tetra encryption algorithm. And of course, you know, it starts with T, so it must be tetra. Anything else is apparently not, I don't know, not perceivable to the people who write these specs. TR1 is generally available. Generally available means not that it is openly specified. Generally available means equipment implementing this algorithm in a closed source and closed whatever manner can be sold regularly and can be sold worldwide without restriction. It's the original algorithm. It has very relaxed export conditions. TR2 is only for public safety users in the Schengen and European Union area. The custodian of this algorithm is the Dutch police. And if you want to get access to that algorithm, you need to write to the Dutch police and explain why you should be eligible to receive a copy of the specification. Interestingly, on eBay, quite frequently, you can find Tetra phones with TR2. It's like, interesting. Most of them seem to come from Spain. I don't know whether policemen are selling their radios there because, I don't know, because they need money. I don't know. I know Spain is going through hard times economically, but not sure why you see these radios on eBay. It's quite surprising. Then they have specified TR3 for public safety users outside the Schengen and European Union countries. And there's TR4, which is sort of an improved version of TR1. And it reflects the post-1998 Wassenaar Agreement changes. Wassenaar Agreement is the contract that regulates crypto export internationally. It's assumed at least that the original ciphers are 80-bit stream ciphers, but as I said, none of them has ever been leaked publicly or documented, so it's a lot of, I don't know, a lot of speculation what's going on. Well, this is how the individual keys and so on again work together and how OTAR fits into the picture. I'm going to skip over that. As I said, for what we do practically, it wasn't really that relevant. So getting back to the question on how secure is Tetra, well, it's much better than GSM. It offers much better security functionality, but all of it is optional. And the security of a given network depends even more on the configuration of that network than in a GSM network. And if you look at the reality, then it's pretty sad. The government networks are secure, at least in many cases. I have heard that in Belgium, the police radio network, for example, is completely unencrypted, which, well, some people may consider a feature. Well, you know, FM radio was unencrypted, so why encrypt the digital radio? Huh? But the private networks are typically insecure. I have not seen any private network so far which was really configured in a secure way, but that's, of course, limited to some experience in Central Europe. You know, might be completely different in the Middle East, for example. There might be secure networks in the private sector. And I think the first ones to blame are the vendors of the equipment, because it's not like in GSM, you buy a phone and it has all the algorithms and it depends on whether the network uses them or not. But it's every algorithm you want to install in your handset is of extra cost. Right? You buy the handset and it doesn't support any crypto, and if you want to have crypto, then you have to pay something like 100 to 200 euros extra to install the crypto firmware into the device, which, yeah, of course, then many private networks, they think about the cost implications. If you have 1,000 users and you pay 100 euros or 200 euros for each of them, it's a lot of money. And that's not all. If you want to do cryptographic authentication, of course, you need an authentication center in your core network, and they, again, cash in pretty big on those devices. So a lot of networks not only do not use crypto, but they also don't use authentication, because they can also save a lot of money by not deploying an authentication center. The result of that is that all you need to do is you have to have a Tetra handset, and you need to be able to program it correctly, in a sense, configure it correctly to have the parameters of the network, and then you can become a member of the network. Because if there's no encryption, there's no authentication, that's all it needs to participate in the network. But it's not like GSM, where all these features are exposed to the general user. Right? I've never seen a Tetra handset where you can do a network search and manually select a network and that kind of stuff. It doesn't exist. So you need to have some special vendor tools, and you need to sort of tweak them to believe that they are in a factory and they're not outside of the factory, and twiddle a bits and pieces in some Windows DLLs and some Microsoft SQL databases, and suddenly you can change all these things in the handsets. But that's fairly widely known. It's not really something new that we did here. A very interesting case study is tetrahamburg.de, which is a German network covering the city of Hamburg and the surrounding vicinity. Well, this is from one of their marketing material. Blah, 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 blah. It basically says the security is in the foreground, right? The security is a prime feature. And contrary to the existing radio system, the radio connection is digital and therefore safe from interception. Right? It's digital; nobody can intercept it. It's digital, right? Nobody has ever done interception of digital signals before. It's yes. So what is Tetra Hamburg? It's a private company operating a citywide Tetra network, and it's available for paying users. It's like a cellular carrier for GSM, but for Tetra. You can go there, you can buy SIM cards, you can get a flat rate for voice calls or for data services, and you can use it. There is a DFP Tetra Hamburg Gesellschaft für Digitalfunk mit begrenzter Haftung. It's the title of the company that operates it. I'm not sure what DFP means in the beginning. The website claims, well, it's secure because it's digital, and the network does not use any form of encryption, and all the signaling voice SDS. I haven't mentioned SDS before, yeah. But I mentioned that Tetra always needs to name things a little bit different. Who can come up? What is SDS? Yeah, it's the short data service. No, short datagram service or something like that. It's not a short message service, it's just completely different. It has the same restrictions, the same length, it uses the same alphabet for encoding, but it's different. So what you need is a digital radio receiver and a protocol decoder in order to do eavesdropping on Tetra, that's sort of all you need to intercept this Tetra Hamburg network. Another case study is the Berlin subway system, BVG. They have a private Tetra network which connects all the drivers of the subway trains with the central dispatcher. It also connects it with rangieren of English. Any idea? Well, when they prepare trains and put the wagons together and so on, I don't know what the English term is, but for this kind of dispatching? Switching. Okay. Okay. Okay, for switching, interesting. So for switching also they use that, and yeah, it doesn't use any form of encryption. All the signaling is transmitted in plain text. So once again, you need the digital radio receiver, protocol decoder, and so on in order to decode it. That they use tetra is again something they don't even really publicly disclose. You have to dig a bit and find out that some of the equipment manufacturers, they say, we got the contract of BVG for tetra equipment, and now we know that they use tetra. So yeah, you need that receiver, and you need to go there, and you need some software, and you can decode it. Interestingly, the speech codec has a reference implementation available from Etsy. So that's, of course, if you want to intercept speech traffic. Decoding the radio, demodulating the signal, doing the decoding of the protocol stack is one part, but the other is the speech codec. And luckily, with Tetra, the speech codec has been, there's a reference implementation. So not only do you have the spec to implement it, but you have C source code that you can compile, and it will decode it. SDS, the short data system, short data service, I mentioned it already. The other thing that Tetra offers, of course, it has something that is like GPRS, but actually they call it slightly different. They call it packet data. And they use SNDCP, the Sub-Network Dependent Convergence Protocol. Very nice name, could come from a Star Trek episode. You have to remodulate your Sub-Network Dependent Convergence Protocol. But this is actually used in GPRS too. It's the same protocol. So they reuse some of the features here. You can do IPv4 or even IPv6 over Tetra if you want using that. But beware, 36 kilobits is the maximum bitrate on standard old Tetra equipment. So it's really, really slow. So if you see those kind of I don't know, the press releases the police makes, we will have mobile data services and we will be able to download fingerprints into our Tetra handsets and so on. 36 kilobits. That will be very exciting. Yeah, it has PDP contexts and APN names and so on. It's really GPRS, but just for Tetra networks. It's very, very slow. If they don't support these QAM modulation and Tetra 2 features, which, as I said, are not very, very widespread. Okay, getting to Osmocom Tetra, it's a software project for demodulating, decoding, and protocol analyzing Tetra air interface. Basically, we have 3 programs which are all very, very big but functional hacks. It's also the fact that it's 3 programs, not 1, is sort of a result of that. You have a USRP or some other software-defined radio receiver. There's a much more convenient device called the FunCube dongle, which is a small USB key that you plug into your system. It's USB powered. You don't need the big bulky USRP and the power supply and so on. It looks like a DVB receiver, some TV receiver or something like that. You have a program called tetra demod.py, which is a Python script using a lot of existing GNU radio code to do the actual demodulation, and it writes float values of the individual symbols into a file. Then we have a program called float to bits, which converts from float values into actual bits, basically doing the differential decode. And then we have another program called tetra-rx, which reads that bits file, and it gives you some output to the console about the protocol decode, and it also generates GSM tab messages that you can feed into Wireshark, and there's a Wireshark tetra dissector, so you can actually look at the protocol traces in Wireshark this way. Don't be irritated that it uses GSM tab. It wasn't worth creating a tetra tab format and again registering a port. We just reuse GSM tab. It's not really worth. The demodulator is a code reuse from the AppCo25 software receiver project, which some people, I think, in either Australia or New Zealand were hacking on. So surprisingly, the Tetra system used in the rest of the world and the AppCo25 project used in Northern America used the same modulation, and therefore you can use the same code to modulate and demodulate it. They call it differently. Like if you Google for it, you would never come up with the idea that they use the same system, because in Tetra it's called pi quarter DPQSK, differential DQPSK, and in AppCo it's called CQPSK, yeah. C is for compatible. So they say it's a compatible QPSK. I wonder what's compatible with. So we had already these GNU radio blocks. It has a root-raised cosine filter, an MPSK receiver, Costas loop, Miller and Miller synchronizer. If somebody of you is into digital signal processing and software-defined radio, those things will tell you. We get these float values. The physical layer we implemented does the burst synchronization by locking onto training sequences in certain frames. It does the normal both, first on a sync burst, then on normal bursts, and it splits the payload from the training sequences. Then there's a burst generator as well, which does the inverse step. So we almost have everything for transmitting as well, because that's how you test your own code. You have to first artificially generate tetra bit patterns, then you can feed them into your just created decoder, and after that works, you go to real signals. So we have a lot of the transmit side as well. The lower Mac does all the things. As I said, it's very, I personally was very excited when I looked into all of this, because it taught me a lot about communication systems, and particularly error correction coding and so on. So I now understand fully what rate compatible punctured convolutional codes are. Yeah, that kind of stuff. There is the transmit side as well. We haven't ever used that code to actually transmit on the radio frequency, but we can generate bit patterns that we can feed into the decoder. So I think it would be very easy to actually use that to transmit as well. We have the upper MEC, which is a receive-only implementation, and you get some dumps of the messages. And it's mainly proof of concept, but it works very well. I've done quite extensive decoding over multiple days of tetra traffic. It's not a problem at all. The LLC, again, is a receive only. It does the defragmentation and so on, and we can recombine the frames and feed them into, for example, SNDCP. So if somebody uses IP services over tetra, we can actually decode them up to the point where you see the inner IP packets in Wireshark, which is fairly convenient. But unfortunately, all I've seen it being used for is NTP so far. So if for days and days and days you look at it, it's like, okay, somebody's sending NTP requests. Great. Well, it doesn't really seem to be used much, the data services. Many networks already advertise that they don't support data services anyway. So there's no point even trying to look for data like M2M, machine-to-machine communication. The GSM-TAP header has been extended for tetra support, and it outputs this signal so you can catch it with Wireshark, similar to what AirProbe does, similar to what Osmocom BB does. It's basically the same thing, just for tetra. The Wireshark decoders, yeah, I didn't really want to write any of that, and I still don't want to write any of that, because the tetra protocols are all, well, bit-packed. So nothing is ever byte aligned. You always have bit length fields, and you have variable length bit fields with like something like a 5-bit length field indicating the length in bits of something else that follows after it. It's really ugly. And they have not formally specified it, so it's not as easy as just getting an ASN1 spec from the tetra specification, putting it in the ASN1 compiler and getting a parser for it. Nope. But the Beijing Institute of Technology has developed a Wireshark dissector, and they wrote an IEEE paper about it, and I found the paper and I emailed them and they released the code. So actually now we have cleaned that up a little bit, and it's already in Wireshark mainline. So Wireshark has tetra decoding, thanks to the Beijing University, who is of course working with Chinese industry in creating tetra systems. So transmitting, as I said, almost everything is there. Somebody could do that. I think we have all the low-level parts to create a tetra base station we should have. It's mostly the higher level, the logic like call control and so on that's missing. It would be an interesting project to create something like OpenBTS for tetra. I myself am not very interested in that. Also, a lot of the other guys in the project are not really excited about it. Because we actually have some real-world tetra base stations, some real like Motorola and so on equipment that we would rather play with before we go anywhere like this. There's some thanks slides. and I'm going to show you a bit about the commercial tetra radio equipment that we have. It's all just the public wiki. You can just check out tetra.osmocom.org, and you can look that up for yourself. So we managed to get some Motorola EBTSs, and we have PCB photographs of all the different boards that go in there and how they work, and the bootloader, and some dumps of the serial console you get when you use that equipment. This is the diversity receiver used in the system. This is the exciter that actually generates and modulates the signals. And the integrated site controller is also an interesting piece of hardware. It's all from the late 1990s. It's a Power PC mainboard with ISA slots, something I've never seen before, but apparently it was sort of fashionable at Motorola in the late 1990s. And you have boards that are still full of, large integrated circuits, something I haven't seen since my teenage years. And you have a good old Tulip-based Ethernet card, PCI Ethernet card with, look at the connector, right? Also something I've never seen before. As in a PCI Tulip chip card which only has 10 base 2. It doesn't even have 10 base TX. Sorry? Yeah, I could solder it. I know. But I think I have other things to do in my spare time. So, okay, this is sort of where we stand with Osmocom Tetra. We have the software-defined receiver, demodulator, decoder, protocol analyzer. I can show you some traces in just a minute. As I said, we haven't really anything for transmitting yet. We are doing some research on the handset side as well, doing some reverse engineering of handsets to understand them better. It's quite funny that, for example, Motorola again have features where the central dispatcher of a police station, they can adjust the volume of individual radios that the policemen have in the field. So let's say you call somebody and he doesn't respond, you can increase his volume. So maybe he hears you next time. I hope they don't do that with undercover agents though. But it's quite interesting to integrate such a feature. So this is not part of the Tetra spec, but it's vendor-specific proprietary additions that they have added to it. And of course, it would be interesting to understand more how they work and what they're doing. Okay. Before I'm going to show some stuff here, maybe we can take questions. If you want to raise questions, please go to the microphone and speak into the microphone for the benefit of our streaming viewers and people who view the recordings.
Even though I'm afraid that the precision of the answer might not satisfy the auditorium, could you give us some perspective on how far the analysis of the crypto part of Tetra has advanced so far?
I'm not a cryptographer. I'm not a crypto analyst. I've never been to a university. It's no, I mean, there are some people looking at it, but that's all I can say. It's not really something I'm personally involved with. I guess we'll have to wait some more time for that. Just to give you some idea, though, the Tetra specified encryption, the TEA, is only the air encryption. The German networks, for example, for public safety users, they use 2 layers of encryption. They first have the radio, the air interface encryption, and then they use end-to-end encryption on top of that. So even if, at least for German government networks, even if somebody was to find significant flaws in the air interface encryption, you still have that additional end-to-end encryption layer. I think it's a hard, in German we say a hard nut, so something something you will bite a long time, you will chew a long time to get into. Personally, I'm not very optimistic on that, but there are many other Tetra networks out there which are not secure. So,
is that specific to TEA2, or are there multiple layers also for the other 3 standards?
The second layer, the end-to-end encryption, is completely independent of whether you use any air interface encryption or which one you use. It's completely independent. It mostly depends on what are the capabilities of your handsets, and which translates into how much money you're wanting to invest into your handsets. But otherwise, it's completely unrelated. So you could have a network that only uses end-to-end encryption and no radio encryption. Another thing that's maybe interesting, I forgot to mention it, is that if a network uses air interface encryption, you will not even see what's called the ITSI, which sounds a bit funny. It's the IMSI of the Tetra network, right? There has to be a T in it, otherwise it wouldn't be Tetra, so it's the ITSI. There's also the GITSI, which is a group group Tetra subscriber identifier, the GITSI. And so even those identifiers are encrypted, right? So if you go to a GSM network, even if the GSM network uses encryption, you will always see those identifiers if and when they are transmitted over the air interface. But with Tetra, even those identifiers are already encrypted by the common cipher, the CCK, the common cipher key. So really, it's not that bad what they did, but a lot of people just don't use it. Next question, yeah.
So what's the difference to the EADS tetrapol system?
Tetrapol is an entirely different system. It just somehow borrows the name. It uses different modulation, different channel spacing, different encoding, different bursts, different multiplex, different protocols. It's like a completely different system. They tried to make it as widely adopted and as how can I say, as official a standard as Tetra, but they failed. I think it's mostly being used by French police these days, but otherwise I'm not aware of really that much widespread use of Tetrapol. Interestingly, in Berlin, the trams use Tetrapol while the subway uses Tetra.
Have you looked into TEDS, the Tetra Enhanced Data Service?
Sorry, the?
TEDS, the Enhanced Data Service, so you get faster data rates.
Yeah, I haven't. We haven't implemented it in our Osmocom Tetra, and I haven't seen it in any of the networks that I've seen, which is mostly limited to Germany, of course. Do you have any idea where TEDS is being deployed?
I think some networks in the UK are using it.
Ah, okay, yeah. Yeah, I haven't. I mean, it's the higher level protocols are exactly identical. It's the modulation that changes and the channel bandwidth that changes, and some bits of the lower MAC layer that change. But it's I don't think it would be, at least for the 8 PSK version, it would probably be easy. For the other one, I'm not sure. Maybe a week full-time work or something like that to add that. It's not it's not an unrealistic thing to do if somebody was interested and has some idea about digital modulation and so on. Next question. Was there a next question?
Have you taken a look at key extractions from the handsets? Because most handsets in voluntary parts of the catastrophic relief systems are physically unprotected.
Yeah, this is why typically at least in government-related or emergency or safety services-related networks, the key material is all stored in the SIM card. And you get to smart card security, which we've heard quite a bit about. But the handsets themselves typically don't store security-related material. I mean, there are some cheaper handsets which don't use a SIM card, but those you will not find in sensitive networks. They always use SIM cards for storing the key material. Otherwise, the handsets themselves, they're fairly difficult to get into. It starts with, at least I only know the Motorola handsets a bit. It starts with that they use a very strange DSP architecture. I think it's called Red Cap or something like that. It's I've not seen it being used anywhere else, so you need to get familiar with an instruction set that you've never seen before, and they encrypt their firmware images, and it's all highly proprietary. A lot of automatically generated code. It's not a nice environment to play with compared to other embedded devices that you might have worked with. Okay, we're running out of time. I hope it was somewhat interesting. I definitely encourage everyone to continue to look at security of communication systems and security of IT systems outside what you consider typically IT. Don't look at the internet. Don't look at the desktop PC. Don't look at servers. Don't look at TCP/IP. You know, there are thousands and thousands of other people looking at it. But how many people are looking at tetra security? How many people are looking at RFID security? How many people are looking at these kind of systems? There are other systems in use. There's tetrapol, for example, which nonetheless might be something interesting to research. We just started to look into Raya and other satellite telephony systems. They, of course, have, again, their own protocols, their own security implications or lack of security implications. Right? I've never seen anyone giving a talk about applied research on satellite telephony. Why not? I mean, it's just another system. The specification is public. You can download it. You can read it. Please do something else than internet security. Thank you.